I can see your presentation file as well. So you can
Oh,
start when you are ready.
okay. So, so my name is Yongkan Xu. I'm professor at UCLA. First, I need thank you for detail and the weather program office give us opportunity to present our work. Um, so for this study, basically is on the GUX LS4P project. We try to propose a new mechanism for the S2S prediction. It will Tibetan Plateau, Rocky Mountain, the wave trend, TRC we call. So we basically try to use high mountain temperature to do the S2S prediction. So there are many the collaborators, and this project started from May 2018 in the last GX sign open meeting in Canada. So basically, we try to improve the initialization of large scale land surface over high mountain like Tibetan Plateau, Rocky Mountain, to improve the S2S prediction. So this project we have many organizations include like ECMWF, NCEF, and so many France, Japan, and China. So many meteorological organizations. We have about 20 Earth system model, about 10 regional models. So I first need to just address one issue because in many people's mind, they feel the land temperature only has very short memory, only can last for a couple of days. How can do the sub-seasonal seasonal prediction? So here is the data we from the camps. We choose the colder May and the warm May, we do a difference. Then you find when the May in Tibetan Plateau, for instance, is warm, this warm actually could last several months, actually start from December. In Rocky Mountain, like you have a warm May, it also can last at least for 3 months. So there is a long memory. Because in most places, the soil temperature only they measure to like 25 centimeter. There's originally was no observed evidence to support this land memory. But in Tibetan Plateau, there was like here we have 80 stations. So among them, like 16 stations that measure to 350. So that's that's the profile. So it's the difference between the warm year and the cold year, warm May and cold May. So you will see this kind of structure, and based on this structure, based on you can use any formula equation to calculate the memory. There is a memory for several months. Furthermore, there is data analysis show based upon observed T2 with the temperature and observe the precipitation. We do the MCA analysis, the maximum the covariance analysis. So previously we called SVD analysis. So show it's for the first modes show in the West US when the May was warm, then in June to the southern US, in the coastal area will be wet, to the northern part will be dry. If it's colder, then we opposite. For the Tibetan Plateau, it's if the temperature in May is cold, then in June it will be the drought to the source of Yangtze River and wet to the north. So I have to point out here the temperature modes in US. This is the second EOF modes. For the precipitation, actually this is the first EOF mode. So these are the major climate modes. So based upon this relationship, we did quite a number of studies, and actually, we did for 2003, because 2003 Tibetan Plateau was very cold, to the south of Yangtze River was dry, to the north was wet, and people never find out what's causing this drought. And for the GWAX phase 1, we choose this case because when the GWAX S4P start the project, actually our original purpose was see, because these results actually was reproduced by the UCL GFS model. So they want to see if other model can reproduce this kind of results. Cold temperature produces drought and wet condition here. So the issue is, in current situation, most Earth system model in high mountain, there has very large bias. Here is an example. So we use the China meteorology administration's data as a tool because they have more than 80 stations around here. In most analysis data, observation data in here, the data only from GTS is about 20. So we have more stations here with your tools. So we look at climatology. 2003 was a cold year. In 1998 was a warm year. Then you will see even the observational data like CAMS, CRU, in particular CRU has a quite like a difference from the CMA data. And in reanalysis, only ERA show more close the number with the observation CMA. Like in other the reanalysis, they all have a larger bias. So that's why at this point we found that when we have LS4B data, so the model that do the control run, we found that there's a larger systematic bias. Suppose like May 2003 should be cold, and the model example mean show it's a warm bias. And actually, we originally only look at for the East Asia. So it should be dry, but it's actually with a wet bias. But actually, later we found that actually in other parts, like in North America, it's same thing. In North America, June 2003, coastal area was quite wet. To the north was very dry, but the bias is opposite. So because every model at the point in high mountain has a bias. So we develop some kind of methodology. And for instance, for May 2003, it was a cold anomaly and model has warm bias. Then we impose a mask, make the temperature to correct this warm bias. So it was for initial condition. Then after we impose this mask, the model produce at least with a cold anomaly, although it's not as cold as observed, but it is cold. After model produces this cold anomaly, then we found so this is global observed anomaly in June 2003. Then we found in 8 areas over the world. So those areas show the example, show the significant the difference between with and without this mask. So then find it's a produced anomaly consistent with the observation. In particularly, actually, we originally, as I mentioned, original purpose will produce a drought to the south of the Yangtze River. Then we found in North America, they also show a very consistent with observation. So we identify 8 hotspots over the world that produce after model produce the cold anomaly in Cabinet Plateau in May that can produce observe the June precipitation anomaly. So that's what we identify as 8 hotspots. Of course, some review they say you should not only stick on consistent with observation. For instance, in Siberia, there also actually is significant, but it's opposite to observation. But we'll not talk about this at this point. But the question is, people ask why these hotspots. The reason why there is those kind of geographical distribution is because the Tibetan Plateau and the Rocky Mountain temperature here. So we use 5 warm and 5 cold May. So you will see, in particular, in the spring and the winter, May especially, you will see an opposite anomaly. Then this is correlation show this opposite anomaly is statistic significance and is statistic significance. So then we base upon the Tibetan Plateau temperature anomaly, we do a regress to the geopotential high at 200 millibar. We found that there is a wave trend start from Tibetan Plateau, go to Northeast Asia, so cross the Bering Sea, then when reach North America, become 2 branches, one to the south, one continue to the east, then back to the Tibetan Plateau. So if we look at this, you will see this hotspot region, except that this is Africa, 2 hotspots. There were along this hotspot region, or in the extension, like in the northern part of South America, is in the extension. So that's why this geographic distribution was produced. And also, particularly, it was a very surprise was that because we first focus on the East Asia. So in East Asia, the model show more consistency. That was not a surprise. But in North America, actually, no modern group look at this. But when we get the results, we found that it's very consistent, as long as it's along this wave trend. For the Africa, actually, the relation between Tibetan Plateau and Sahel, that's not discovered by the AS4P. I think many study, data analysis show the upstream relationship. So at the meantime, we also did the comparison with SAT using 2003 observed the ST. Then we found that the ST can produce 6 hotspots. In most areas, there is a kind of different from the Tibetan Plateau effects. Only in Southern Grand Plain, both play the similar role. So the Tibetan Plateau land-surface temperature, subsurface temperature anomaly normally generate, in most parts, generate like so 25% to 40–50% an observed anomaly. The SAT in most area also produce 25% to 50%. So it shows both play a very similar role. So then we further do analysis that was published in the climate dynamics, a special issue for AS4P. It shows this the model with adequate Tibetan Plateau, Rocky Mountain wave trend. In particular, you can see this opposite phase. So those groups basically produce more anomaly compared with the modern group, this 5 model, they actually produce same phase here. So the anomaly with the bad the Tibetan Rocky Mountain circumglobal wave trend, it's produced more anomaly. So this is one evidence to show it's the importance of this Tibetan Plateau Rocky Mountain wave trend. And also that was from GOE S2S model. So because they found that so initial condition, their model actually initial condition did not produce the wave trend very well. You can see Tibetan Plateau Rocky Mountain is the same phase. So they're using a nudge method, start from April, then nudge till May 1 to produce the initial condition with the proper wave trend. Then you will see in East Asia with the wave trend, so produce observed anomaly to the source of the Yangtze River. So without a proper wave trend, it didn't produce any anomaly. In North America, coastal area, also with proper wave trend, it's a produced observed anomaly. But so this again shows the Tibetan Plateau Rocky Mountain TRC play an important role in the S2S prediction. So those work we basically publish in the GMD, introduce AS4P, a project, equipment design. Then the major results we publish in BAMS and also in a climate dynamics special issue. At this point, we now move to the phase 2. Phase 2 will focus on the Rocky Mountain. And so Rocky Mountain effects and the Rocky Mountain and the Tibetan Plateau interactions to in particularly their effects on the drought in June in South Grand Plain and flooding in Yangtze River. So in 1998, it was a very warm May in Tibetan Plateau. It's an extreme cold temperature in Western US. So in Yangtze River, it was a heavy flooding. To the south of Grand Plain, to actual coastal area. So US, it was very dry. So we try to produce this relationship, this kind of the flooding and the drought based on this temperature anomaly in Rocky Mountain and the Tibetan Plateau. And here I show some very preliminary results. One from ECMWF. They show, for instance, in Tibetan Plateau in 1998, originally, it should be a warm temperature, but in the model they have a cold bias, very cold. So they have imposed a mask. They have some, the mask, we have some tuning parameters. So we try to improve the mask. So they improve the mask, they produce a warm temperature here. Then they also, it's original in Yangtze River, should be flooding. It was very, cold, very dry bias. So now they can produce the wet condition to the source of the Yangtze River. And another one, we from UCLA NCEP GFS SIV2. When we impose the Rocky Mountain mask, then you can see it's produce a dry condition to the south and a wet condition to the north. And Alaska also is kind of wet. And actually, if you along the wave trend, you can see this part anomaly is consistent. And also the Rocky Mountain produce the flooding in the source of the Yangtze River. Here is a table shows, for instance, for the Yangtze River, observed anomaly is 3 millimeters per day. For the Rocky Mountain, it's produced about 1 millimeter per day in the southern Yangtze River flooding. And Tibetan Plateau produced 1.4. SAT produced 1, comparable to the Rocky Mountain. For Southern Grand Plain, it was dry, and Rocky Mountain produced half of the drought. Tibetan Plateau produced a little bit less than half. SAT did not produce this drought. So it shows the high mountain temperature is a first order effect to produce those kind of flooding and drought. And in the LS4P2, we already encourage each group to expand these results, not only say to the 1998, but to other years and seasons, and not only May, June, but go to the August. So here I show you an example. This year, I think some of you may be aware, in China, there was a heavy flooding and a heat wave, heavy flooding to the source of Yangtze River, and heat wave to the source, to the north of Yangtze River. So the Tibetan Plateau, this is CAMS, Tibetan temperature, temperature in May. Based on this temperature, you can see this kind of structure is a typical LS4P case. Warm temperature produces very heavy flooding to the source of Yangtze River and dry to the north. So we actually we already work on this, and even now June has not finished. I think we can report by August show this case was associated with this Tibetan Plateau anomaly. And the previous speaker team talked about atmospheric river. Actually, we also did some study for the winter case, for the California flooding in 2017, 2023. We found that those are also associated with the Tibetan Plateau anomaly and this Tibetan Plateau Rocky Mountain wave trend. So this anomaly can produce a very nice, actually, the atmospheric river as Tim showed in his slides. So that is the thing we are currently doing, and this is the summary. We show the observation data show a potential for landscape temperature, subsurface temperature should be in high mountain to provide a land memory at S2S time scale. Here I want to emphasize high mountain because there was observed temperature anomaly in the lowland, like in S4P, some group, for instance, Korea group test many areas low elevation temperature anomaly, but they found only Tibetan Plateau temperature anomaly play a very dominant role. So there is the data show the temperature in high mountain is an important play to produce the lag relationship. And also in LS4P, we found using Tibetan Plateau, this is LS4P1 for 2003 case with the Tibetan Plateau, May temperature produce 25 to 40% observed anomaly in most hotspot region. It's comparable to SAT effects. And this kind of influence is underscored by the observed autumn phase oscillation between Tibetan Plateau and the Rocky Mountain surface temperature and the downstream TRC wave trend. So that is the main thing. And so far, LS4P, we still we are studying, and it's still going on. So we are welcome more group. If you are interested, you can participate or this phase. This LS4P, the model experiments, we expect to finish by the end of 2025. So there's still time for you to participate. Okay, so that's all I talked today. Thank you again for the NOAA Software Program Office.
All right. Thank you, Yun Kang. Thank you for your presentation today. So, any questions from the audience? You can unmute your microphone and then ask question to Young King. Okay. Again, feel free to drop any questions or comments in the discussion document I repost in the chat box. So Young King, I have a comment. So I believe NASA maintains a High Mountain Asia HIMAT program. I posted in the discussion document. So I believe your modeling activity would complement the satellite observations in the Tibetan
Oh,
plateau.
yes, certainly. Because I think we first have to use observational data to support the hypothesis. Second is we try to use the, to initialization to better get a better so observed anomaly. So those kind of so initialization, we also need so observational data to support. So this and like satellite so program for high mountain, it's kind of is a very so complementary. We support each other.
Yeah. So another aspect is HIMAT also has because your focus is in the climate modeling. So HIMAT support one of the Landsat's modeling, like hydrologic models, so which can also complement your climate perspective, I believe. So,
Oh yes, and in so next week, so GWAX will have another open science meeting. We will communicate with many, the program, and we try to, complement each other. Like GWAX, there's under so class a program. They're also, they're now also studying the Lancet temperature issues. So they will present. So certainly this work need to have a lot of communication with different projects. We can support each, complement each other.
yeah, I'm glad to hear that. Okay, thank you, Young Kang. A sincere thank you to our esteemed speakers for their valuable insight today. And remember, speakers will continue to engage with the discussion document post-webinar. So please feel free to add your questions and comments for further discourse. Both presentations and recordings will be archived on the NOAA Week 3-4 S2S website, accessible through the link provided in the chat. Again, let's meet again on October 7th at 2 p.m. Eastern Time to skip 2 months. Thank you very much. Bye.